Hello and welcome to this GCSE Physics revision video looking at calculating energy stores and energy transfers. We're going to look at some of the equations used to calculate the energy stored when lifting, moving, stretching or heating objects, as well as energy transferred when work is done electrically and mechanically. If you've watched the first video in this energy series, you'll know that energy is purely a mathematical concept and is measured in joules. No, not that sort. Joules, spelt Joules. Before we start, it would be a really good idea to remind ourselves about some of the quantities and units used in physics, particularly those that we're going to see in this video. Why not grab a pen and piece of paper now and click pause in a few seconds and see if you can complete the table. I'll do the first row for you so that you know what to do. You can see here that the symbol for mass is a lowercase m. The unit is the kilogram and the unit has the symbol kg. Please make sure you're careful about the units. For any of the equations in physics to work, we have to ensure that all of the quantities are stated in the internationally standard units, or SI units they're called. So for example, if a question talks about a mass of 43 grams, the first thing you should do is convert this to 0.043 kilograms by dividing by 1,000. Be really careful because the exam boards do love to try and catch you out. If you are going to pause and see if you can complete the table first, please do it now. The remaining quantities with their symbols and SI units are shown here. You will need to know these, so test yourself regularly. Those of you who have watched the first video in this energy series will have seen this list before. It shows all of the 9 energy stores and the 4 energy transfer pathways. GCSE Physics requires that you can calculate the 4 stores of kinetic, gravitational potential, elastic potential and thermal, along with 2 of the transfer pathways, electrical and mechanical work. Let's look at the transfer pathways first. Whenever energy is transferred from one store to another, we can say that work is being done. Work can either be electrical, which involves the flow of charged particles such as electrons, or work can be mechanical, which is characterized by the use of forces to make objects move. The quantity of work being done will be equal to the energy being transferred, so work and energy must have the same units, i.e. joules. No. If we take a look at mechanical work then, the equation we need in order to calculate how much mechanical work is being done is force times distance moved in the direction of the force, or W equals Fd. So mechanical work is really easy to calculate. We simply multiply the force, in newtons don't forget, by the distance moved in meters. Don't forget to convert to these units if they're not already done so for you. Slightly more tricky are the questions that give you the work done and the force applied and ask you to calculate the distance moved. Or maybe they ask you to find out the force exerted. So here we're going to need to rearrange this equation in order to make the other terms the subject of the equation. In this case, force is equal to the work divided by the distance, and distance is equal to work divided by force. I'm not keen on those formula triangles, because I'd much prefer you were able to rearrange mathematical equations for yourself. However, if you do need one, it's here. You can see that work equals force times distance, force equals work over distance, and distance equals work over force. You'll benefit so much by not having to rely on formula triangles, so I do strongly suggest that you revise the sections of your GCSE maths which cover rearranging formulae. If we now look at electrical work, the equation we need to calculate work done as electrons carry energy from a cell to a lamp or other component is potential difference multiplied by current multiplied by time, or W equals VIT. Again, make sure the quantities are in the correct SI units and simply multiply the 3 together. You're allowed a calculator, so make sure you use it. Be careful though, because questions do exist that ask you to calculate any of the 4 quantities as long as they give you enough information about the other 3. So make sure you can rearrange the equation to make each quantity the subject of the equation. So potential difference will equal work divided by current times time. Current equals work divided by potential difference times time. And time is equal to work over potential difference times current. The formula triangle for this is trickier, but it does still work if you need it. Another way of looking at electrical work is by remembering that potential difference multiplied by current is equal to power. So therefore we could replace the VI in the first equation with power to give us work equals power times time, or W equals PT. Lastly, we could also view electrical work in another way. If we recall that the quantity of charge flowing past a point in the circuit is equal to current multiplied by time taken, or Q equals IT, then this will give us work equals potential difference multiplied by charge, or W equals VQ. To summarise the energy transfer equations so far then, there are 4 equations that we can use to calculate work done, either mechanically or electrically. If you want a mnemonic for free, you can use mine. Work transfers energy when you put vitamins in food very quickly. Next, we're going to look at the 4 energy stores and how we can calculate the energy stored within them. Remember that if you know how much an energy store has been changed, then you know how much energy has been transferred either from it or to it, or how much work has been done. The kinetic energy store describes energy of moving objects. The faster or heavier the object, the more energy it has. You'll remember that the kinetic energy store can be calculated as half times mass times the square of the velocity, or E equals mv squared over 2. As before though, we may be asked to calculate the mass or the velocity of a moving object if we know its kinetic energy. So here, again, we need to rearrange the equation to make each term the subject. So here then, mass equals 2e divided by v squared, and velocity equals the square root of 2e over m. Putting these equations into a triangle becomes a bit tricky. One way you could do it is like this, but be careful when calculating velocity because you'll have to remember to square root the e over half m. Another way to draw it is like this. I prefer this version because it's easier to remember, but be aware that you'll now be calculating 2e rather than e, so don't forget to halve the result. Gravitational potential energy is the energy gained by an object as it's raised off the ground. It's also the energy released as an object falls from a height. The factors affecting the quantity of energy stored by such objects are the object's mass, the strength of gravity, and the change in height. This gives us the equation to calculate gravitational potential energy as mass times gravitational field strength times height, or E equals mgh. Rearranging the terms in this equation to make each the subject gives us m equals E divided by gh, and h equals E divided by mg. The triangle in this case will have 4 terms in it, so be careful. The strength of the gravitational field, or G, here on Earth is 9.81 newtons per kilogram. You'll often be told what value to use for G in the question, but be prepared to either use 9.81, 9.8, or sometimes you'll just be told to use a value of 10 newtons per kilogram. The elastic potential energy store describes the energy stored in an object as it is stretched or compressed. If we stretch a spring or a rubber band and then let it go, it will return to its original shape. The work we do on the spring can also be transferred to another object at a later time. This is how wind-up clocks and catapults work. So how do we calculate the quantity of energy transferred to a spring? Well, by stretching a spring, we're applying a force over a distance. So we can use the very first equation described in this video, which calculates mechanical work done by multiplying force and distance. However, things aren't quite as easy as that. It gets more and more difficult to stretch a spring the more it is stretched. At first, the spring requires very little force to extend it. Later, as the spring gets longer, the force required to not only hold it, but extend it further increases. If we plot extension against force, we get a line graph like this one, where the force required to extend the spring increases as the spring extends. The energy transferred to the spring can then be shown as the area under this graph. You'll remember from maths, the formula for the area of a triangle is half base times height, which gives us an equation for the elastic potential energy as E equals Fx divided by 2, where x is the extension of the spring. The gradient of this graph is called the spring constant and is given the symbol K. The gradient describes the stiffness of the spring and shows us how much force is required to extend the spring by 1 meter. It offers a good way of comparing springs with one another. A spring with a high spring constant is very stiff. It takes a lot of force to extend it even a little bit. Whereas a low spring constant describes a spring that is easy to extend. Calculating the gradient can be done by simply dividing the force by the extension. Rearranging this equation to make force the subject gives us F equals kx. By replacing the force in the first equation by kx from the second equation, we get a third equation of E equals kx squared over 2. So now we have 3 equations linking spring constant, force or energy. We just have to choose which one allows us to answer the question. The last 2 equations relate to the thermal store of energy. The thermal store will increase or decrease as the temperature of the object increases or decreases. The equation we need to calculate thermal energy in this way is mass times specific heat capacity times temperature change, or E equals mc delta T. Specific heat capacity is a property of a substance. It describes how quickly its temperature changes as we add or remove thermal energy to it or from it. The higher the specific heat capacity of a substance, the more energy you need to add to it in order to raise its temperature. Water has a high specific heat capacity, which is why it takes forever to boil your kettle, especially when you watch it. Again, the exam question writers may try to be a bit sneaky and ask you to calculate mass or temperature change, so you'll need to know the rearrangements of the equation as for all the others so far. This gives us m equals E divided by C delta T, C equals E over M delta T, and T equals E over MC. The thermal energy store doesn't just depend on temperature. The state of a substance is also important. Remember that the temperature of a substance doesn't change as it's melting, yet the energy is still being transferred to it. This energy is being used to break the bonds between the solid particles in order to turn them into a liquid. This is the reason that temperature doesn't increase despite the substance still being heated. Specific latent heat is a measure of the quantity of energy it takes to change the state of a kilogram of a substance from a solid to a liquid, for example. The energy required to melt a substance then can be calculated as mass times specific latent heat, or E equals ml. Rearranging gives us m equals E divided by L, or L equals E over m. I've presented quite a few equations to you in this video, and I'm sure you've forgotten some, all of them already. I've summarised them all here, organised into those that calculate energy transfers or work done, and those that calculate changes to energy stores. You do need to learn these equations and how to rearrange them. A good way of doing this is to put each one onto a flashcard. On one side of the card, write the names of the quantities involved in the equation. On the other side, write the equation itself and all of the rearrangements, and the formula triangle if you find this helps you. Then test yourself. Ask friends to test you, ask family, and do it often. You'll also need to learn all the names, symbols, and the units of all the quantities involved. If you follow these really simple rules for answering the calculation style questions, you can gain a whole bunch of marks that actually a lot of students don't even bother trying to get. It always amazes me that so many students see a mathematical calculation question and just leave it blank. Yet by following these simple steps, you can't really go wrong. First of all, make sure you read the question. Sounds obvious, doesn't it? But you'd be surprised by the number of students who, once they've opted to attempt it, fail to read what it's actually asking. Then identify the quantities given to you and the quantity asked from you. Actually write these down. Next is to write down the equation that links all these quantities together and rearrange it so the quantity you've been asked for is the subject. Then substitute the values given in the question, not forgetting to use the correct SI units. Finally, use your calculator to produce the answer, rounding it correctly if necessary. The key now is for you to practice, practice, practice. Oh, and practice. There are loads of examples and past papers on my website, plutoniumscience.com, or on the exam board websites themselves. Don't just stick to your own exam board. Use questions from the others as well. It gives you much more variety. So that's it for now. Make sure you stay in touch for some great science content, new material or revision tips. If you have the energy, you can contact me via my website, plutoniumscience.com, or follow me on Twitter at PU94Science, or you could just email me directly. Keep up the good work and good luck with the exams. Before I go, I'll leave you with this. If power is the rate at which energy is transferred from one store to another, according to the equation power equals energy divided by time, then what is the unit of power? Send me any comments you have. Take care.